Equilibrium is a balanced state that stays balanced unless something knocks it out of balance. Sometimes it's pretty clear that you're watching a movie in reverse. But we can tell now that time is back to normal, driving systems into equilibrium. Equilibrium comes from Latin words for equal and balance. At equilibrium, opposing forces are equal, balance each other out, and guarantee that these balls will stay where they are.
Almost anywhere I throw the balls, they settle into this one lowest valley, and they won't escape the valley. Gravity is pulling them down to the point with the lowest potential energy. At high points, they will have high potential energy from gravity, and will use this energy to move towards the lower energy valleys. It's the lowest valley, but it's not the only place the balls might settle. Some balls never make it to the lowest point. Instead, they settle in a different valley, in this corner. What's so special about these places? Each of these valleys is a stable equilibrium. Now I'll attempt to change where the balls land. I'll shift the landscape, which will change the equilibrium. There's a new lowest point, and the old lowest point is one of the highest points now. In this new configuration, they settle in a different equilibrium. I've successfully shifted where the equilibrium lies.
This type of equilibrium where nothing moves is a static equilibrium. All of the parts of the system are motionless, static, and the forces are balanced, in equilibrium. But sometimes, even when opposing forces balance each other, small parts of the system still move. In dynamic equilibrium, the state of the system is the average of its parts. The average state can stay the same, even if small parts change. For example, an individual coin can either be up and spinning, or down. The state of the system is how many coins are up. I can spin coins so that 3 coins are spinning at once. As soon as I spin up another one, friction knocks down one of the ones that was already spinning. So even though individual coins are changing from spinning to not spinning, or from not spinning to spinning, the overall state of the system, how many coins are up, 3, stays the same. That's why we call it equilibrium. How do I shift this kind of equilibrium? I can either change the rate that the table slows them down, or change the rate that I spin them up. I enlisted my sister's help because together we can spin coins up at a faster rate than me alone. It turns out that together we can spin fast enough for a dynamic equilibrium of about 5 coins up at a time. We've successfully shifted the equilibrium of the system. So how is this actually working? My sister Claire and I can spin coins up faster than I could alone. To balance this, friction needs to knock coins down faster too. This happens when friction has more spinning coins on the table to knock down. So the new equilibrium happens when there are 5 coins up and the rest are down. At 5 coins up, Claire and I can spin up a coin at the same rate that it takes friction to knock one down. So we're left at a stable dynamic equilibrium of 5 coins up. As time runs forward, we're driven towards equilibrium, where opposing forces are balanced and opposing rates are equal. But we can shift where the equilibria lie, either by adjusting the rates at which individual objects switch state, or by changing the landscape.